very much, Vaidu, for the introduction. Yeah, and now today, welcome to everyone to our today's UNIFI seminar fall series webinar. And my topic today will be the potentials and challenges for grid forming solutions in public power grids. I will try to give you an industry perspective on this topic. We at SMA, we appreciate the US UNIFI initiative to increase the pace for the integration of inverter-based grid forming solutions into public power grids. Since SMA also has a strong interest in the establishment of grid forming battery energy storage system in the US power systems and also worldwide. So some disclaimer from the legal department of SMA. And then to the agenda. So what is it about today? So I will give an overview over SMA and its solution portfolio that we have. I will explain the current drivers for grid forming solutions. We'll say some words on the design considerations. We'll present you the grid forming system concept and control from SMA. And we'll give you also some project experience that we did within the past years within research and development projects and other projects that were very important in our development in grid forming. And last but not least, I will point out the need for an adequate grid forming framework on how, from SMA's perspective, it should be designed in an effective way. So let's start about SMA, of course. Who is SMA? For those of you who have not been in touch with SMA in the past, we are a high-tech energy transition company in the power conversion business and a pioneer for decarbonization and decentralization, and this for more than 40 years, since 1981. For those who are interested, can visit our website, 40years.sma.de. Some numbers about SMA. So our total installed capacity of solar inverters is about 125 gigawatts worldwide, installed in over 200 countries. And also within the last years, 5 gigawatts of installed battery inverters came additionally to it. And the solar energy and the inverters help to avoid carbon emissions of around about 86 million tons per year. Our technology is protected by over 1,600 patents and utility models. Over 3,600 employees are working on new solutions for the energy transition, and this happens in our subsidiaries in over 20 countries in this world. So our company is segmented into 3 segments. It is home, commercial, and industrial segment, and large-scale segment, and 5 sectors. And our core business is still the PV system technology. We have also a growing contribution into storage, market integration, and since 2020, we entered also the electromobility business for home and commercial industrial solutions, and also the power to gas business. So we provide electrolyzers support or conversion systems for power to gas applications. Some key numbers, maybe you see compared to the last year. This year we will nearly double our sales and our income. Our inverter power that we sell year by year, so within the last year at least, it will be almost 12 gigawatts. And now we see a high growth, high increase. And so that we built now our second SMA gigawatt factory that will almost double the today's production capacity in our headquarters. And the last week we also announced that SMA will expand also manufacturing into the US. That will add additional 3.2 gigawatts per year in production from 2025. So what is the SMA portfolio? The SMA portfolio covers all stages of energy integration and enables our customers to participate in the energy system of tomorrow, even today. What do we offer? We offer a solution for generation and efficient use for storage and flexible use of solar energy. Solutions for being able to refuel your electric cars with solar energy, to heat and cool with solar energy, to generate hydrogen for electrolysis application, with solar power to manage distribute energy, sell and trade easy. And the most important part that the topic will cover today is stabilize grids and be 100% grid independent. Yeah. And what we offer is high quality PV inverter system for storage applications, but also beyond charging solutions, also services, software, apps for energy management, and also operation and maintenance services for solar power plants and also storage power plants. So what are the drivers for the grid forming solutions in public power grids that we see and face? So solar power, storage systems, and also digitalization are revolutionizing the world of energy, and energy is becoming sustainable, independent, and decentralized. We see that solar power within the last years became the cheapest source of electricity in many regions, and storage system and digital solutions balance out generation and consumption. And this enables households and businesses to share their electricity with other customers. And due to the fact that the solar power is now the most cost-effective source of electrical energy, conventional generators are more and more plugged off the grid. And we see a tremendous growth in PV installation that is continuously increasing. And with increase of PV installations, since PV power plants can only produce power during the daytime. And if we want to build up renewable energy systems with a high renewable share, then of course for PV systems, we need also storage to shift the energy to times when the sun is not shining. And consequently also the storage systems that compensate for fluctuations of solar power, they are also growing very fast. And this transition towards renewable energy generation, this requires a minimum stability service provision in network regions with low or even no synchronous generation running. So we come from a power system which was centralized, where the conventional power plants with their synchronous generators, with their voltage source behavior, with the inertial behavior, fault current contribution, overload capabilities, short-term, long-term storage capabilities, dynamic, active and reactive power reserves provision, island grid operability capabilities, and also capability for grid restoration and black start. But this inherent grid forming services of synchronous power plants becoming less, because the conventional power plants are phased out of the grids. And on the other side, of course, renewable energies are on the rise. They provide the cost-efficient, carbon-free energy to the power systems and act typically as a current source that enables for maximum carbon emission reduction. They operate in a grid following way, and today support but not form the power grids of the systems. One of the reasons is their dependence or the intermittent power availability, because if the sun is shining, you have power that you might use for some kind of stability services. If the sun is not shining, then at least for the active power, it is really, you need some kind of energy storage for provide with, but conventional renewable generators, especially photovoltaic power plants, have not the same capabilities as conventional generators have. They initially were built for energy generation, not for grid stabilization. Grid stability is a part that is coming now more and more. And let's say very important to have a minimum stability service provision in network regions where it is required, where there are no voltage sources. And the energy transitions is leading to some regional shortfalls in transport capacity. So there are shortages in power capacity that can be transported through a power grid. For example, if at some nodes there is a lot of renewable generation that wants to be transported, or where the grid following inverters push the available power into the power grids, which operates more and more at their limits. Additionally, also there are shortfalls in inertia due to the fact that synchronous generators are operating at not all the time, maybe, or not at that amount that is required, let's say, to ensure minimum levels of inertia. The same is valid also for the short circuit current and also for the system strength and voltage quality. And the services that are today inherently provided by the synchronous machine-based power plants need somehow to be provided also by other grid participants in the power grids. And we believe strongly that grid forming capable energy storage system will replace rotating machines in public electricity grids. And thereby they will solve two major challenges. That is, let's say, very important for energy systems with a high share of PV generation. And this is the energy shifting. So to shift the energy to the times when it is needed and to stabilize the power systems in case it is needed. Yeah, and this is also our, let's say, best practice for years. That in this way we see also the future, and our systems are built this way that the PV systems are made for cost-efficient carbon-free energy generation, and the energy storage provides all the capabilities and have all the technical, let's say, prerequisites that are capable to substitute the capabilities of conventional power plants of today. Now looking into the design considerations regarding grid forming design. So what is grid forming? And from our perspective, grid forming incorporates the grid forming services that can be provided, but must not necessarily be provided by inverter-based resources like PV power plants or wind power plants. And this can include the following capabilities. First of all, a voltage source behavior. So someone needs to provide the voltage reference and the angle reference for grid following sources and also grid following loads and grid following storage. It is also the instantaneous response to grid events or to load changes, the capability for synchronization with other voltage sources and for load sharing, capability to provide inertia for limiting voltage vector shift, capability for provision of damping to oscillations that occur in the grid. That might have different reasons. Of course, own damping is always required, but here it means the damping that is, let's say, needed for oscillations that result from interactions in the grids. Voltage quality improvement capability, so not necessarily to ensure an own voltage provision, but to improve a voltage quality whenever the voltage quality is poor. Uninterruptible power supply capability, black start capability, synchronous short circuit fault level contribution, system strength enhancement in the grids. Yeah, these are the, let's say, the capabilities that might be more or less required or demanded by the markets. And there might be some markets where there is low demand. There might be some markets where there is high demand. So, for example, on the left, if you look of at-home systems that we will see also on some slides later, then for your home system, inertia capability might not be very important. Damping, of course, is somehow important, for example, of voltage quality improvements, but uninterruptible power supply capability might be not that necessary. So it could be also okay if, in case of a power outage, your local grid goes down, and after some time, you would like to have a power supply again. Yeah, so there are some, in summary, some requirements for some of the applications like island system realizations or even grid service stability provision, where some of the requirements for grid forming system might be essential, and in other case might be nice to have, but not really mandatory. An important aspect for grid forming system design is that the grid forming control action requires a suitable design. Yes, so inertia provision, synchronization provision typically requires or has as a consequence a power exchange with the grid. Yeah, and this power exchange requires some reserves for being provided. This might include static and transient power and energy reserves, in addition to other services that you would like to provide with your power plant. And it also requires some headroom to consider, current and voltage headroom, not only at the AC side, where you would like to provide your grid forming capability, but you need also to care about the DC side and the DC source on the behavior and the dynamics on it for being able to perform grid forming control action. Suitable design is also required because load profiles determine the component stress. So you might have very high disturbance conditions at the point of connection of your power plant that provides grid forming services. And here, the load stress will depend on one side on the worst case scenarios that you would like to ride through in a grid forming manner with maximum support. And on the other side, also on the scope of service extent. So on how much grid forming service you would like to provide on your compensation objectives. Yeah. Another aspect that is important within grid forming design is that the components your system is built of need to match with each other. So that means the inverters, the source or storage, the transformers, switching elements, auxiliary equipment, everything need to match for being able to provide the grid forming services in a required manner or in a manner that you would like to do this. Looking at the SMA's offering components for component systems and solutions that we provide in a grid forming manner. So on one side, we have home systems or grid forming capable components and systems for home customers. On the left side, you see applications that are provided by our some of our PV inverters for home applications and also by our storage inverters for home application. It's called a secure power supply for home systems. And this means that these systems, in case of a power outages, have an outlet, so a socket where you can connect a load to and supply this load by PV power as long as the PV power is available. So as long as the sun is shining, and if the sun does not provide enough power, then of course you cannot supply the load that is connected to your outlet. If you would like to do it more secure, more firm, then we offer also some battery backup systems that are capable to form a household grid at utility grid failure after a short switch over time. You might have a manual switch where you switch to this operation manually, or it might also happen automatically depending on the system extent. And here the loads are supplied by the battery with the support by energy from the PV. Then including to our offering are also hybrid system technologies for off-grid systems that enable autonomous island grid establishment in the range of kilowatt to megawatt with a large shares of PV. And we have also fuel-saving hybrid system management solutions that enable to save any forms of fuels. And on the last side, we also provide grid forming solution for on-grid applications with our advanced grid forming solutions for grid stability services, like for inertia provision or short circuit current provision in public power grids. Yeah, and if you look at today's market-driven voluntary grid forming requirements, we see that the systems that are provided at home they meet, or their requirements level is let's say low, while the requirements for the on-grid applications are quite high. So looking at the SMA grid forming system concept and control, how does it look like? How is it built off? And I will explain it on the grid forming solution concept for our battery energy storage systems at utility scale. So on one side, we have perfectly matching system components where the inverter acts as a voltage source and the transformer acts as an impedance, of course, with the impedances within the inverter. We have also a medium voltage switchgear that also fits to our solution, and this can be scaled up and provides also some flexibility. So that means that you can connect any battery storage that you would like to it, and also accompany it with a plant controller and grid management system for plant level control. On the other side of the system, we provide our enhanced grid forming controls that lets the system behaves as a true voltage source with an instantaneous response, where we have a voltage waveform controller that enables to form the voltage waveform at the inverter terminals. It enables for synchronous operation with adjustable response that I will explain on the next slide. It provides an overload protection control and also capabilities with our power plant manager, so the plant controller from SMA for accurate control with a harmonized interaction at power plant level. And with this solution, it is possible to enhance renewable power plants with grid forming capabilities. And yeah, as I said, it leaves a high degree of flexibility for customization and expandability. So with our solution, we provide the different types of responses to, let's say, to grid events, or different control modes. We call them the inertia control mode and the droop control mode. And I would like to explain you the difference based on this, let's say, a diagram here. So we have on the upper side the frequency. So as a grid, let's say, grid quantity or grid disturbance that is constant first. And then it is somehow changed with a constant rock-off and some deviation. And the red curve describes you the grid angle. Yeah. So the angle of this voltage vector U2, this is the grid voltage vector, while the U1 with the angle are the inverter side voltage vectors. And on in the lower plots, you see the active power response. With this dotted line is the active power reference, and you see here, okay, the behavior at power set point response, so at reference response behavior. So then we have a negative rock-off response behavior, frequency deviation response behavior, positive rock-off response, and an angle jump response behavior. So there are, let's say, multiple ways how our inverter can respond to grid events of a different type. Yeah, there are infinite number of trajectories that we can choose to achieve a finite state that is also to be defined, let's say. And we provide with our control 2 of them. And these 2 control modes are characteristic in the way that they provide a response to the frequency deviations. As you see here, in case of a droop control mode, where the resulting power response is proportional to the frequency deviation from a frequency reference value, let's say. In that case, it could be 50 Hertz. Yeah. So if there is a frequency deviation from this reference value of frequency, then the inverter would provide an active power response that is proportional to the droop constant. And on the other side, we have the inertia control mode, where the active power response in that case is proportional to the frequency gradient, so the rock-off, the rate of change of frequency, and an inertia constant H that is adjustable at inverter level. So we see both kinds of response are instantaneous. Yeah, so they provide an instantaneous type of response, but with different response times or response behaviors regarding, in that case, the frequency changes. The droop control provides, let's say, static response to frequency deviations, while the inertia response provides only a transient response to frequency deviations, but a static response to permanent frequency changes in that case. We in that case, it is possible also, let's say, with our controls to combine both responses, yeah, so that they acting simultaneously. And for power grid stabilization, of course, you need both of them. But the advantage of our control mechanism are that we are capable to separately distinguish between these two and to adjust them independently, which might be very effective in provision of grid forming services of different types to the power system. We did some tests, some laboratory tests within one of our research projects. It was Grid Control to Zero. Maybe you've heard about it. We published also some papers on that, and we wanted, or the goal of this test was to show, okay, how do different control modes of an inverter impact the frequency stabilization in a low inertia power system. How do they impact on the frequency deviation, on the rate of change of frequency, and the vector shift when we operate the inverters in different control modes. And here you see the laboratory setup on the left side. It consists of a diesel generator of 462 kVA that has a very low inertia constant of 0.65 seconds, so H. And it incorporates also all the necessary mechanisms that are needed for inertia provision, for frequency containment, and also for frequency restoration, so primary and secondary reserves. And this way it represents a low inertia power system in our case. And we apply now a power imbalance to this low inertia power system with a load of 60 kilowatts. So it's approximately 13% of the diesel Gen Z power, 13%. And on the other side, we have connected an inverter system to it via a transformer in that case. And this is a downrated Sunny Central storage inverter in our case that we have operated in different control modes. So the control modes have been grid following control mode, so GFL. Then grid following control mode with frequency containment reserve. So that means primary frequency response, but in a grid following way. Then we operated the inverter in a grid forming mode with a droop control, and in grid forming mode with inertia control with the respective H constant. So it's a quite high inertia constant and the droop constant here of minus 0.4 Hertz per unit active power. And what do we see on the right side? So these are the responses now in frequency on the upper side, the response of active power response of the inverter, and also the active power response of the diesel generator, which represents the grid. And we see here, okay, in the grid following case, the frequency deviation is quite high, and also the rock-off is very high in that case. And afterwards, the frequency is getting back and restored by the diesel generators and its secondary control mechanisms. We see that the inverter itself at this load step event with a resulting angular jump, let's say at that point, it almost does not respond to this grid event with any power. Yeah, there is some oscillation, some small equalization or resynchronization, let's say, with the new grid conditions. And we say that the diesel generator absorbs all the instantaneous power that happens at this load imbalance event. And due to this, let's say, power consumption that is taken over completely by the diesel generator, we see a high rock-off response, and this is a high rock-off, and this is due to the very low inertia constant in our power system. If we operate our inverter with also in grid following mode, but with some frequency containment reserve, so primary control, which has some delay, and the delay in the response was almost 2 seconds. So that we see, okay, in that case, our inverter provides some response. It detects, it measures the frequency, and based on this frequency and the adjusted droop slope, it provides some power, but with some delay, so that we see, okay, instantaneously our diesel generator here in that case again absorbs most of the power. But since the inverter also starts to react at some point, the deviation is not that high. The frequency gradient is still the same, the initial one, but our frequency nadir is not that high compared to the case where we have no frequency containment reserves available. If we now operate our system in grid forming mode with a droop control, we see that the inverter responding and absorbing a huge amount of power imbalance that happens in the grid, and this is almost a 13% as we see from the load. And this power that is absorbed by the inverter is not seen anymore by the diesel generator. And since the diesel generator does not see the power imbalance, its let's say rate of change of frequency and change in its frequency is quite small. Yeah, and this seems to be in our laboratory test the best result for frequency stabilization. But this kind of results requires a huge, or at least with these settings that we have chosen here, a huge amount of power that needs to be reserved for being able to provide such kind of response, and a huge amount of energy, which is under this curve here, under this power curve. And the last response is grid forming control with inertia. And we see again, there is an instantaneous response, an instantaneous absorption of power. But according to our inertia constant, as is adjusted afterwards, the inverter tries to reduce the power to the previous, let's say, set point value in that case. And the rest is taken over by the synchronous generator that somehow interacts with the inertia, with the inverter system. But nevertheless, it is capable to reduce the rock-off significantly and also the nadir compared to the grid following cases. And this shows us also the value that we obtain here from the grid forming, from the different grid forming control behaviors. Yeah, that's to the difference. Similar principles are also applicable to the voltage part, so voltage reactive power part. So there it is also possible to adjust an inertial behavior and also a droop behavior within our inverters. Now I would like to come to some experience from the pioneering projects that we did with SMA, this grid forming technology, just to show you some examples. And the very first example that I would like to show is an example from Kythnos Island in Greece. So SMA from the very beginning started to work on the realization of renewable energy systems and participated in the world's first Europe's first wind diesel hybrid systems. Where we provided on one side a central control unit that was built by SMA and also our Sunny Island inverters. So the grid forming inverters that we put into operation in 2001 that allow a simple design and stabilization of island grids by connection of all components on the AC side. So it's an AC coupled battery storage system. This Sunny Island inverters are one-phase units, but they can be operated also in three-phase parallel operation. And using this droop control, that example have shown that kilowatts systems or island systems with very high renewable share are possible even 20 years ago. And since then, we have sold over 130,000 Sunny Island battery inverters that are installed and operate reliably all across the globe in island grids. The second example is that I would like to show you is that of the island of Saint Eustatius. Maybe many of you heard about it. We tried to adopt it also to the megawatt scale and brought the capabilities from our sunny island inverters to our sunny central storage inverters, and have shown in this project, which was awarded at the Intersolar, that the power supply with 100% renewable generation from PV and battery storage for more than 10.5 hours per day is possible. The key findings, let's say, of this project, you can read it everything in the papers. That's one of them is provided here. And at the end, I will also show you or share with you additional papers. Our key findings here in this project were that the inverter-based systems enable a stable power system operation with and also completely without rotating machine technology, also at megawatt scale. Yeah, this is very important because there are many people outside who do not believe that it is possible, but it is. And another important finding is that, as we see here on top, that inverter-based systems allow, or grid-forming system at least, allow superior restoration dynamics after significant grid events like system splits and also grid faults. Yeah. Dynamic processes that take minutes in the public power systems with conventional equipment and its inertia and all the dynamics that it has can be accelerated by inverter-based systems and by far more. So you see here a restoration within 3 seconds compared to maybe 1, 2, or 3 or 5 minutes in the public power grids. Another impressive example is that from a German village called Bordis Home. So there was in the year 2019 an experiment where with our SMAs, Sunny Central Storage Inverters, it was possible to disconnect a 7,500 inhabitants village from the utility grid and supply it with 100% renewable energy from PV, biomass, and battery for 1 hour before you reconnect it again. So here on the bottom, you see the frequency of the island grids and the frequency on where we were connected to the public power grids. And it shows you the superior frequency and not voltage quality is not shown here, but there's also a superior voltage quality in this microgrid operation compared to the grid tie operation. That shows the potential that we have with inverter-based systems if we design them adequately. Yeah, we can improve the power system quality, and it only will depend on the degree of our requirements. Yeah, how qualitative do we want it to have? Another key finding was that the seamless intended transition from interconnected grid operation to and also back synchronization. And the important part here was that the consumers within the grid, but also the renewable generators haven't noticed the transition. And that means also we had also some grid following systems like PV systems within this grid. And their islanding detection mechanisms have not detected an island situation. Yeah, so that means that grid forming in distribution grids can impact on the islanding detection of inverter-based resources, and this is very important to consider for future how to deal with it, because grid forming has always, let's say, contradictory goals. Yeah, we want to establish power grids, we don't want to shut down them. And we need to find ways to make decisions how to deal with it in distribution grids where it is required for fast islanding detection and disconnection. Another impressive project that I would like to present is, maybe you've heard it, is the Red House Scotland project. There was a research project called Distributed Restart, where there was a first live trial that proved that battery restoration in practice works. Yeah. Also, our Sunny Central Storage Inverters were part of this the project, and the technical goals of the live trial that was performed there few months ago. So it's not far away. 2 months ago, I think. It's to demonstrate that the non-synchronous battery energy storage systems, and I don't like this non-synchronous term, that they are able to restart the distribution restoration zones. And another goal was to reduce the restoration time frame from days to maybe hours. So, and it was very successful, this test. The key findings were that battery energy storage systems can be used as an anchor to start, maintain, and control the power islands with or without diesel. And that battery energy storage can also energize distribution and transmission transformers and power lines. And there also an interesting observation was done that point-on-wave switching was recommended to avoid some oscillations. And also the block load pickup capability of battery energy storage system is far superior compared to the of synchronous generators. Yeah, because battery energy storage system can pick up to 100% of the load, while conventional generators are only capable for pick up 10 to 50% typically. Read everything in the report, which is available now. And the last example that I would like to give you is regarding the world's first large-scale grid-forming asset that is to provide commercial stability services for the transmission system. It will be built in Black Hillock in the next year. And there was a stability tender in the United Kingdom, the Stability Pathfinder project, the second part of it at least. They requested for short circuit, or the grid operator requested for short circuit level of 11.5 gigawatt amperes, and also for inertia of 6.7 gigawatt seconds. And the winners have been chosen out of 225, 5 synchronous condensers and 5 battery energy storage systems. And we see the shares, let's say, that they cover is that 35% of the inertia is covered by the synchrons, and 65% by battery energy storage systems. So it seems to be more efficient, more effective to provide inertia by battery energy storage systems compared to synchrons. And on the other side, the short circuit level provision is more at the synchron side compared to the battery storage side. But if you compare the annual costs, for the provision of the services, we see that the total provision of both services from BES is much cheaper than from synchron. Yeah? And this shows us, okay, inertia and short circuit level specific costs can be lower for BES. Yeah? And how to achieve it, what is important, and this were the learnings from this project, is that the system planning should have demand-oriented procurement that ensures availability of the right amount of stability service in the right location and in time. Market designs with predictable incentives for firm stability service provision in combination with energy shifting is a key contribution to a cost-effective energy transition. And technology agnostic voluntary specifications define the service quality and enable for market participation. Yeah, these 3 elements are very important. So define requirements is very important. To have a demand-oriented procurement of services, because otherwise it's inefficient. And market designs can help to make it even cost efficient. But it needs to be firm. Otherwise, if it's not firm, you cannot rely on such a service. Okay, I will come to my last chapter. And this is the need for a grid forming framework that we see. So now, if you look at the thoughts regarding grid forming requirements and provision and so on, we see there are different approaches. One approach, like for example, for some parts of the Finnish grid is, okay, for grid forming services, we would not like to give some incentives, to give some compensation of it. Power plants should provide it by their own. It's like it should be mandatory. Yeah. Then there are some approaches in Australia where is the no harm policy. So that means, okay, if you want to connect your a new power system to the power grids, you need to show that you do not harm. And if you harm, then you need to pay the costs for, or somehow to improve it, that you do not harm the system. And in the United Kingdom, we see a different approach, and this is remuneration. Yeah, so they initially try to introduce stability service markets that are demand-oriented. And if you look on the effectiveness, yeah, on the system stability, yeah, if you have mandatory requirements where all should provide something without any incentives, then the industry will try to give less as possible. And if it gives less as possible, the effect on system stability, of course, is not that much. The highest effect we would achieve if it is remunerated, and if it's remunerated, you can also demand what you would like to have, the quality of power supply and response, and it is the best way and the most effective also in our opinion how systems should be realized. Here, this slide shows, from our perspective, what should be defined as a grid code and what should be defined as a mark design. As a grid code, of course, a minimum level of robustment and write-through capabilities are somehow necessary. Yeah, this is inevitable to achieve a stable power system. Also, protection and settings of this protection is very important. Minimum levels of power quality, limited voltage control, and reactive power capability that is needed for power fit-in, and of course some requirements on large signal frequency controls on emergency situations like the LFSM mechanisms for over and under frequency, for example. Market design would be appropriate if there would be a node-specific need and market creation for reactive power contribution, fault current contribution, black start, voltage quality, and also inertia. And from our perspective, there are a lot of ancillary service markets and capacity markets that are working today, which includes the primary frequency reserve market, secondary and tertiary reserve markets. And what is missing and should be introduced are a new stability segment for inertia and short circuit level provision. And the good part is that all of the services can be covered by a battery energy storage system in very efficient ways. For longer duration, of course, you need another type of storage, but many problems can be solved by battery energy storage systems, which and their share in power grids will increase by time. So I come to my last slide as a summary. So as we have seen, grid forming technology for large-scale IBRs generating system is already available today. Battery energy storage system will solve two major challenges in future power systems, and it is stability and energy shiftings to times when it is needed. This is key to a clean, stable, resilient, and affordable power system supply. And the ability to meet the market-specific requirements with a system design flexibility is very important and can be met with our systems. And our grid forming solution enables also for multiple revenue streams and high profitability with your asset. Yes, that's it. Last but not least, also for further reading, some references, our papers, so papers of projects where our equipment was used for you. And now I'm open for questions. Thank you very much.
Okay, thank you very much for the interesting presentation. As I have done a lot of work on this grid forming